Here's an interesting geometry problem. Pause the video and give it a try. All right, here's one way to solve it. Now, when you're asked to find an area, I always recommend writing down the areas you know at the start because it's easy to build up areas from components. And there's a parallelogram in the middle here that we are basically just given the area of. We're given two sides and we're given an angle. So we can write that down right away. The area of this parallelogram is going to be just 10 times 12 times the sine of 75. So area of the small parallelogram is the product of the sides times the sine of the angle. And if you work it out, that comes out to about 116. So let's just leave that there for now. Now for solving the problem, notice that the midpoints of various lines are being connected. Like the midpoint of this line is being connected with the midpoint of that line. And when you're connecting midpoints, you might want to remember a little fact about triangles, sometimes called the triangle midpoint theorem, that if you take any triangle, whatever it is, and you connect the midpoints of two sides, like so, then you get parallel lines. That midpoint line is parallel to the third side of the triangle. So keeping that fact in mind, let's make a useful triangle for this problem. Let's draw a line from A to C. So that's going to be a triangle that helps. And let's also draw now a midpoint line from this midpoint here to the midpoint of A and C. So these two sides here are equal length. So that's right here is the midpoint of AC. So what that means by the midpoint theorem we just talked about is that red line is actually parallel to this line down here. But we could do the same thing. We could make a red line coming up from this point, and by the same theorem, that line is parallel to this leg of this triangle. And so in fact, this little shape on the left here is a parallelogram. That shape is a parallelogram, and so the side opposite to each other are equal, and so that side is of tick length 1, and this side is of tick length 2. And now we see that this red triangle here is actually congruent to this blue triangle here, because they're just halves of a parallelogram. They share all three sides of equal length. So we can say that the red triangle is congruent to the blue triangle, and that means that the area of the red triangle is equal to the area of the blue triangle. And now we're basically there, because we could have done this whole exercise with other triangles. We worked on this left blue triangle and red triangle, but we could similarly have drawn this one down here, that blue triangle, and this red triangle, right? And we could have gone all the way around the parallelogram and filled it up, done the same thing with this blue triangle, and this red triangle, and finally the last one, we have a blue triangle on top, and we have an opposing red triangle. And although the areas of each of those triangles might be different, the blue one, the area of the blue one, is always equal to the corresponding area of the red one. Okay, so the area of the 4 red triangles is just equal to the area of that inner parallelogram and equal to the area of the 4 blue triangles. So that means that the whole parallelogram, so the area of ABCD, which is what we're asked to calculate, well, that's just the area of the 4 reds plus the area of the 4 blues. And since the area of the 4 reds is equal to the area of 4 blues, well, they're each contributing exactly 1/2 to it. This thing, the area of the 4 reds, well, we already calculated that. That's 116. That's the first thing we did at the very beginning of the problem. And what about the area of the 4 blues? Well, it's exactly the same because we just proved that. So it's 116 plus 116, 232. Or if you want the exact answer, it's just twice the exact area of the small one, which is 240 times the sine of 75 degrees.